Hello, everyone. Welcome to the presentation of FLASH, Federated Learning for Automated Selection of High-Band Millimeter Wave Sectors. My name is Batool Salehi. I am one of the authors and a PhD student at Northeastern University. Matrix communication is one of the key aspects of next-generation standards, and it includes applications such as advanced driver assistance, fully automated driving, traffic efficiency, and infotainment. In all of these applications, we need either low latency or high data rate connectivity for safety reasons or quality of service. And this motivates us for using millimeter wave band for V2X communication. In millimeter wave band, we can achieve data rates in the order of gigabit per second. Moreover, we are using directional transmission with phase antenna arrays to compensate for high penetration loss at high frequencies by concentrating the energy into narrow sectors. You can achieve the promised gigabit per second data rate if you are choosing the right sector for communication. And the method that current standards such as 802.11ad suggests for this sector initialization step is an exhaustive search approach that can take up to tens of milliseconds. As a result, these exhaustive search approaches are not feasible in V2X communication because these cars are moving very fast and the optimum sector can change very rapidly. To address this challenge, we are proposing to use multimodal sensor data for millimeter wave beamforming. First of all, we know that the transmission at millimeter wave band is quasi-optical. This means that the optimum sector depends on the geometry or state of the environment. On the other hand, we know that multiple sensors such as GPS, camera, and LiDAR are now available as a standard installation in vehicles that can provide us with this situational information. As a result, we are proposing to use this sensor information as input to an inference engine to predict the optimum sector. Using this method, we don't need to do exhaustive search anymore. This work falls in the domain of out-of-band beamforming, and the state-of-the-art methods in this field can be categorized into two tracks, RF-based and non-RF-based methods. The first approach in RF-based method is using channel measurement campaigns to characterize the propagation at millimeter wave band. That requires extensive data collection and also domain knowledge. The second approach suggests using measurements in sub-6 GHz band to speed up the millimeter wave beamforming. That can lead to challenges such as hardware limitation and also requiring a mapping to translate the CSI at sub-6 GHz to millimeter wave band. On the other hand, we have the non-RF-based method that use sensor information for millimeter wave beamforming. However, none of the state-of-the-art methods validate their approach on a real-world dataset. Moreover, there are focus on centralized learning that comes with a huge overhead. In our setting, we have multiple vehicles in an environment that want to establish communication with a base station at millimeter wave band. These vehicles are equipped with GPS, LiDAR, and camera sensors, and they are going to use this information to configure the optimum sector for transmission. There are some challenges associated with using this sensor information for millimeter wave beamforming. First of all, we need a paradigm to combine the local sensor data for millimeter wave beamforming. To address this challenge, we are proposing a multimodal fusion technique. The second challenge is that we need to share the knowledge over all vehicles without exposing the local data to outside entities. To address this challenge, we are proposing a multimodal federated learning scheme. The third challenge is that we need to reduce the overhead with respect to current standard. For this challenge, we are comparing the end-to-end sector selection time of our method with 802.11ad standard. And finally, we need to take measures to be sure that our method is resilient to missing information. For this challenge, we are proposing a data adaptation scheme. Our first challenge is having a paradigm to combine all of these sensor information for sector prediction. For this challenge, we are proposing to use multimodal fusion with deep learning models to successfully combine all of this information together. Our fusion network has two main components. We have per-modality feature extractors that are designed based on specific features of each of these sensor inputs. And on the other hand, we have an integration network that gets the output of each of these feature extractors, concatenate those together, and passes those through another setup layer for sector selection. By using fusion network, different modalities can compensate for missing information in others that can result in an increase in accuracy. To share the knowledge among all vehicles in the environment, we are proposing to use federated averaging for distributed learning. A standard federated averaging scheme starts with local training at clients or vehicles in our case. In the next step, the vehicles are going to share their own local model with the base station. The base station then aggregates all of the received local models together and generates the global model. Finally, it shares the global model with the vehicles for the next iteration. By using the federated averaging scheme, we have a distributed learning over all vehicles in the environment. Moreover, we can share the knowledge through federated averaging with low overhead and keeping the data local. And finally, we have a mechanism for sharing the updated model regularly with vehicles. We are proposing an adaptation of a standard federated learning architecture that we refer to as multimodal federated learning. Our proposed framework runs in 5 steps as follows. At the first step, we have the local training at vehicles. As a result, the vehicles are going to use their own local data to train the fusion model from the challenge 1. In the next step, the vehicles are going to share the local fusion model with the MEC. The number of parameters that needs to be exchanged here equals to the number of parameters in each of these individual CNN branches. Moreover, the accumulated overhead over all vehicles scales with the number of vehicles and the number of federated iterations. We have a multimodal orchestration module at the MEC that stochastically selects a branch for aggregation according to a policy. For example, here we are choosing to aggregate the LiDAR branch. In the next step, we are going to perform federated averaging only on the selected branch. And finally, in the downlink, we are going to share the aggregated branch with the vehicles for the next iteration. By using this multimodal orchestration module here, we are reducing the overhead in the downlink by concentrating the update to the selected branch instead of the entire fusion network. In the next iteration of the federated learning, the vehicles are going to replace the received aggregated LiDAR branch with their own local LiDAR branch. And this process repeats over federated iterations. We are validating our Flash framework on a real-world multimodal dataset that we collected at our campus at Northeastern University. Our testbed is located between 2 tall buildings and resembles an urban area. We use an autonomous vehicle for our experiments. Moreover, for millimeter wave radios, we use Talon 87-100 routers that work at 60 GHz with 34 sectors. We get access to the physical layer measurements of this router using the firmware that is released from this paper in the citation. We put one of the routers on top of the vehicle and we put the other one on the cart on the roadside. Our autonomous vehicle has an onboard GPS. Moreover, we mount a GoPro Hero 4 camera on top of the vehicle that is faced towards the base station. And finally, we have a Velodyne LiDAR with 64 channels at the vehicle. All of these sensor modalities are connected to the computer on a vehicle. And for each experiment, we use the iPerf3 software to initiate the rotors as transmitter and receiver and start a stream of data. We collect the RSSI of each of these sectors at the base station, and we also collect the multimodal sensor data at the vehicle. Our flash dataset has 3 unique features. It is the first real-world multimodal federated learning wireless dataset. Moreover, it's in large scale and includes around 32,000 samples. And finally, it's inclusive and contains different categories such as line of sight passing, line of sight with pedestrian, line of sight with a static car, and line of sight with moving car. We compared the performance of our proposed flash framework with 2 other learning-based methods. First, we have the local learning scenario. In this case, the vehicles are going to use their own local data to independently train different models. The error bars in this figure show the variation in the top 1 accuracy across 10 vehicles in our experiment. From this figure, we observe that the maximum accuracy with local learning is 36%. The second competing method is the case of centralized learning. In this scenario, the vehicles must share their own local data with the base station. The base station gathers the local data from all vehicles and then trains the model. In this table, we are reporting the top 1 accuracy as we keep adding more vehicles. And we observe that as we keep adding the vehicles, our accuracy will increase. And the maximum top 1 accuracy in this case is 87%. However, we need to remember that this accuracy comes with the huge overhead of sharing the local data of 10 vehicles with the base station. We are evaluating the performance of our flash framework for 4 different policies. The first one is the case where we update the entire model in the downlink. We have an unbiased policy that randomly selects one of the 4 branches for aggregation. We have a policy that is biased towards LiDAR and integration branches. And finally, we have a greedy LiDAR policy here. From this plot, we see that the maximum top 1 accuracy with flash framework is 68%. To highlight some of the observations from these 3 experiments, we have this table here. We observe that with local learning, the maximum top 1 accuracy is 36%, but we don't have any sort of model or data sharing. With centralized learning, we have the maximum top 1 accuracy of 87%, but we need to share around 2.5 gigabytes of data with the base station. And finally, with flash framework, we get 68% top 1 accuracy with much less overhead. As a result, we are concluding that our flash framework outperforms the local learning by 46% improvement in accuracy and centralized learning by 70% improvement in overhead. We compared the end-to-end sector selection time of our proposed Flash framework with 802.11 ADS standard that uses an exhaustive search approach. Moreover, we include another metric here, the throughput ratio, that characterizes the ratio of throughput when we are choosing the sector that is predicted by model versus the case where we do exhaustive search. From this figure, we observe that our Flash framework improves the sector selection speed by 52%, while it can retain 89% of throughput. Finally, we are evaluating the performance of our proposed framework with respect to resilience to the missing information. We are proposing a data adaptation scheme that replaces the missing samples with the closest previous ones. In this figure, we are comparing the case where all sensor modalities are missing versus the case where only GPS image and LiDAR is missing. And we are plotting the top one accuracy over different loopback steps. From this figure, we observe that the Flash framework can retrieve 67% top one accuracy when up to 10 samples are missing for all modalities. As a conclusion, in this paper, we propose the Flash framework for millimeter wave sector selection. Our method includes sensor fusion to improve the prediction accuracy, federated learning to avoid sharing the local data with the base station with 68% prediction accuracy. Our Flash framework decreases the sector selection time by 52% on average, while it can maintain 89% of throughput. And finally, our method is resilient to the missing information. As the future direction, we are proposing to explore methods to reduce the overhead in the uplink and also a scalability to different code book sizes. Our first of its kind multimodal beamforming dataset with mobile sensors is available at our public dataset repository. Please feel free to check our website and reach out to us if you have any questions. Thank you so much for attending this presentation. I am open to your questions.